So, along came... time dilation is the title of this lesson. We'll talk about what the word dilate means. Along came Uncle Albert to offer the following explanation. And he started with two postulates. A postulate is a statement that you're not going to prove. You're going to assume that it's true and reasonable. And then you're going to say, what can I prove from that? His first postulate, he said this. If two frames of reference move with constant velocity, if you're at a constant velocity, what's your acceleration? Relative to each other. Then the laws of physics will be the same in both frames of reference. Say, what? Here's what he said. Look, if you're in an airplane, in a jet, are you moving at a velocity? Yes or no, if you're in the jet flying through the air. Be obvious. Are you moving at a velocity? Yes. But he said the laws of physics are going to be the same. If you're not accelerating, when you pour the coffee, it's going to go straight down. It's not going to go shooting over your shoulder or up. So if you pour a cup of coffee while on a jet plane that's traveling at 700 kilometers per hour, the coffee pours straight down still. It doesn't pour backwards and then up on your lap. And if you want to try this, if you're in the back seat of a car with somebody else, try playing catch in the back seat. Even though you're moving forward at a constant speed, you don't need to throw the ball forwards and have them move into the ball to catch it. You can just play catch back and forth, the same as if you're on the ground at rest. You won't notice the difference. As long as you're not accelerating. Constant speed. So, in the space below, sketch the path of the ball and what it would look like if it was thrown in the van to an observer who was looking through the glass wall of the van. So the van is driving by, and the person in the van throws it straight up and straight down. The person standing on the road watching the moving object, the object that has a velocity relative to them, what would they see? I'm going to argue that they would see the ball started on the ground inside the van, and I think to them it would look like the ball followed that path because the van is moving forwards while the ball is going straight up and down. You okay with that in your imagination, Cole? You got to use your imagination here a little bit. But Dylan, we're saying if you were standing on the side of a road and you had a van with a glass wall, the person in the van would think that they had tossed the ball straight up and down, but you would see the ball go like that because it's also moving forward while it's moving up and down. Which one is correct? Einstein said both are. Both are. The second postulate of the relativity principle says this. The speed of light is the same for any observer, no matter what the velocity of the observer's frame of reference is. In other words, Christie, he accepted the Michelson-Morley experiment. He said, it doesn't matter whether you're moving towards the light or away from the light, you're not going to measure a different speed. There is no experiment that you can perform that will get a different answer relative to someone else. Fancy word, the speed of light is a word that begins with letter C. I used this word in the last lesson. Huh? Constant. In fact, it's the constant. We're going to use... Okay, my pen is acting up all of a sudden. Good gosh. I don't know why it does that yet. I haven't figured it out. Speed of light is a constant. Speed of light is a constant. That says constant. My pen's acting up. Time dilation. Your time is not necessarily the same as my time. Little note, dilation means make wider or larger. So time dilation means time is lasting longer. Slowing down. According to Einstein's special theory of relativity, a clock that is moving, that says moving, will slow down. And it's slowing down so that we can get the same measurement for time when we go speed is distance over time. So we can't get the same measurement for speed. I said for time. For speed. This stretching is called time dilation. Who remembers, what did I say our acceleration was going to be throughout this topic? 0, okay? We can't accelerate. That gets into general relativity, and Emma, the math for that is... So what we're going to use then, and you can write this down, is this equation right here. It's really d equals VIT plus a half AT squared. But what did we just say A was going to be, Christian? So what happens to the half AT squared? 0. And then, you know what? If you're not changing speed, there is no initial or final velocity. It's just the velocity because it's the same the whole way. Okay? Here is what Einstein imagined. I want you to imagine a spaceship made of glass. And again, I said one of the ways that Einstein was clever with his thought experiments is he said, and I'm going to set up a timer, but the timer, Matteo, is going to be a beam of light. This way I can work special light into my thought process. So we're going to have a beam of light go bing, 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 back and forth. Okay? Is it possible that in two different frames of reference, identical clocks might run differently and that time might pass differently? Yes. This is one of the predictions of Albert Einstein's special theory of relativity. So figure 15.6 illustrates an observer. So we are sitting in space. Let's suppose we're astronauts. Tristan, we're in a space suit. We're floating at rest, and we see a glass spaceship come past us, and we're looking at it through the side. Can you imagine that? It's made especially so an outside observer can watch an experiment being done by an inside observer. The inside observer is watching an event consisting of an imaginary oscillating light beam. Bing, 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 back and forth, back and forth, back and forth. Pause. Wrap your brain around that so far, Joel? Now we're going to get deep. Turn the page. This oscillating light beam acts like a clock. The beam goes up from the source to mirror A and back to mirror B. The inside observer has a really, really accurate stopwatch, and they measure the time that it takes the light. I'm going to really gum up my diagram. Don't write on your diagram. They measure the time that it takes the light to go there as times 0. T with a subscript of 0. And the speed of light is c. So if I want to write an equation for the distance, we would say this. This distance is c times time 0. That is vt. That's this distance right there. Don't write that down, just watch. Now, if I'm the person sitting outside the spaceship, I see the spaceship traveling sideways at a speed v, which means this distance that it travels, which is the same amount of time I see it take for the light beam to go up and down, I measure that as v times t. Now that v is the speed of the spaceship, but it's a distance. So far, so good. Then, I time from my stopwatch how long it takes the beam of light to go from here to there. Now, of course, to me, Nick, I see the beam of light travel that way because the spaceship is moving sideways at the same time as the beam is moving down. So if I wanted to write an expression for the distance that the beam of light travels relative to me, I would say that that distance is the speed of light times the time that I measured on my stopwatch from my spaceship. Don't write all this down. We're going to do a better picture in a second. Okay? So here is my idea. This is what Albert Einstein did in his paper. Christian, this is a distance d in meters. I'm going to get rid of letter D and just leave that expression there. This is a different distance in meters, but I'm going to leave that expression there. This is yet a different distance in meters, but my point is all of those are answers in meters. The units all match, which means since they're in meters, that's actually a triangle. I can use Pythagoras. I told you we were going to use Math 8. So here's the triangle on the next page where it says DULP that we can draw. We're going to draw carefully a right-angled triangle. Free-handed. Try and make it look like a right-angled triangle. And we're going to use the idea that distance is speed times time. Don't write this next bit down. That distance right there, don't write that down. The length of that little vertical line is going to be speed times time. Which speed? Light speed. Which time? Time on board the spaceship. We'll call that T0 or TO, T on board. The base of this triangle, Joel, how long is that? It's going to be speed times time. Which time? The time of us floating in our astronaut suit that we measured on our stopwatch, because we're not on board the spaceship. And then, what do you call the slanty part of a right-angled triangle? It begins with the letter H. Okay, the hypotenuse, that's also going to have a length, and that's going to be, because this is what we're observing, this is what we see the beam of light doing, the speed is going to be the speed of light, c, but the time is going to be what we measure. So these two lengths here are what we observe. That's why it's a T and a T, because it's our stopwatch. The vertical length, Christian, is what the person inside the spaceship times. But they're in a different frame of reference. They're experiencing time different from us. What does Pythagoras say? Anybody remember Pythagoras? Something squared plus something squared equals something squared? And believe it or not, we're going to prove this. That's Math 8. We're going to prove Einstein's theory of special relativity with Math 8. Everybody write down. A squared plus B squared equals C squared. Where A and B are the two short sides. So here's our equation. We're going to have something squared plus something squared equals something squared. There's Pythagoras. What's one of the short sides? CT0. That's a distance. What's the other short side? VT. What's the hypotenuse? CT. It's Sierra Math 8 with a vengeance, but it is Pythagoras. Now what we're going to do is we're going to put the squared onto each term in the brackets. So we're going to write this as little c squared T0 squared plus V squared T squared, and that's going to equal C squared T squared. We would like to get this by itself. How will I move the V squared T squared to the other side? Add, subtract, multiply, or divide. How do you know? You're right. Because what's right in front of the V squared T squared? Plus. Okay? So that's why I wrote here, isolate the C and the T0. So we're going to get this. C squared T0 squared equals C squared T squared minus V squared T squared. I wrote here distribute powers. I actually did that on the very top line. I forgot that I was going to do it later. Distribute powers would be get rid of brackets. Getting deep. Jacqueline, what does it say step 4 is? by c squared. C2, B4, that's battleship. C squared, that's math. With me? So what we're going to do is this. I'll do it in red. Divide by c squared, divide by c squared, divide by c squared. Have we violated equation solving rules, Cole? Did we divide everything by c squared? So we're still on Math 8 firm footing for solving an equation. Why did we do that? Because here, the c squareds cancel, and I get t0 squared. And here, the c squareds cancel, and I get t squared minus v squared t squared over c squared. I know this looks scary, but Maggie, so far we've done Math 8 and Math 9. Yeah, with algebra and Math 8 and Math 9. Maggie, what does step 5 say? Factor out which one? So, see the right-hand side? This right-hand side has, don't write this down, 2 terms. Is there a t squared in this term? Is there a t squared in this term? Who remembers in Math 9, what did you call it when you had something that appeared in everything? It was 3 letters. When you were factoring and you had the same thing appearing in everything, what did you call that? Not greatest common denominator. Yeah, GCF, greatest common factor. I can factor out a GCF. Okay, so you ready? By the way, this is still Math 9. I agree, Joel, we're doing it pretty intensively, but so far we've done Pythagoras and factoring, so it's going to look like this. The t0 squared drops down like a domino. When I factor a t squared out of a t squared, what's left behind? You're right, Sierra. So I'm going to go like this. T squared bracket 1 minus. When I factor a t squared out of a v squared t squared over c squared, what's left behind? I think the v squared over c squared. Last thing we're going to do is we're going to get the letter T by itself. So you can all turn the page. I'll stay right here. Michael, see the T? What's this big ugly bracket doing to the T? Adding, subtracting, multiplying, or dividing?
Multiplying.
So how will I move that big ugly bracket over?
Multiply everything by t
No,
squared.
ready? I want to get the T squared by itself. What's this big ugly bracket doing to the T?
Multiplying.
So how will I move this big ugly bracket over? It's the opposite of multiplying.
Divide.
That's it. And I'm going to get this. Look up, look up, look up. There's going to be a T0 squared, and it's going to be over 1 minus v squared over c squared, and that's going to equal t squared. Let me again emphasize, Christy, I'm not going to make you reproduce this. We've almost got the t by itself. I have a t squared by itself. How to get rid of a squared? Okay, so you ready? The final step is going to be square root that, square root that. Here's our time dilation equation. This is what Einstein published in his paper. He said, it seems to me t equals, what's the square root of t0 squared? What's the square root of x squared? Just x. What's the square root of t0 squared? Just t0. And we're going to leave the bottom in a great big square root like this. Although, if you want to, you can point an arrow to that, and you can say that's also V divided by C all squared. V squared over C squared is the same as V over C all squared. Remember your exponent rules from Math 8 and Math 9. And we need to talk about what these mean. I've given you this massive equation. So you ready? Where T equals time on the stationary object, usually Earth, or the astronaut floating in space at rest when the spaceship zooms past him. T0 equals time on board the moving object. Emma, T0 equals time. What's the word I used? Again, time. What's the word I used? What letter does on board begin with? What letter does that 0 look like? That's how I remember. T-O, T on board. Okay. V is the speed of the moving object. Who remembers what the letter C lowercase stood for? Which constant, though? This was the ultra special one. This is the speed of light. Which is 3 times 10 to the 8th, but we're going to try and be clever, and instead of typing in 3 times 10 to the 8th, we're going to try and do all of our physics, or at least most of our physics, as percentages of light. Let me show you what I mean. By the way, that's the equation that's on the back of your sheet in the first special relativity one there, yeah? T equals T0 over 1 minus V squared over C squared, all square rooted. Yes? On your green sheet? Ready, Emma? Feel like traveling through time? Okay. Now, first thing we need to say is this. Relativistic effects and relativistic speeds only occur when you are relativistic effects only occur when you're approaching relativistic speeds. It's when you're going close to the speed of light. Okay? So in number 1, we're going to ask this. I'm going to skip number 1 and do number 2 first. I keep forgetting to flip-flop these. A spaceship is traveling at 85% of the speed of light. If 1 year passes on the spaceship, how much time passes back on Earth? Jacqueline, is this brand new to us? Say yes. We're going to carefully list our data. So the first question, folks, is, what's this question asking me to find? Now here's the second question. T or T0? Go look at what we wrote. Is that asking us to find T0 or T? Okay. So let's all write down T equals question mark. That must mean they've told us the rest. Did they tell me time on board the spaceship? What? Now the nice thing is Einstein's equations work for whatever units you put in. If we put our numbers in years, we'll get an answer in years. We could convert this to seconds, but did they tell me how fast the spaceship is traveling? Christian, read me the phrase. That's not the phrase. Read me the phrase. No. Starting with 85. What's the phrase? I heard it over here. Okay, what? Loud and proud again. What? Pause. I don't do math. Pause. Look up. I don't do math with percents. I always have to change a percent to a decimal. 85% is what as a decimal? 0.85? Write that down. The word of right after a percentage, does that mean add, subtract, multiply, or divide? Okay, this is one worth filing away. Of means multiply. So we're going to times the speed of light. Sierra, what was the symbol for the speed of light? I'm going to write 85% of the speed of light is 0.85 c. What would I write if it was 60% of the speed of light? 0.6 c. What would I write if it was 99% of the speed of light? 0.99 c. See? Do you see? You see? See. Let's write down the equation. T equals T0 all over square root of 1 minus, and I'm going to write it this way, V over C all squared. I like that one better, as opposed to the V squared over C squared. All right. What was T0? Let's put a 1 there. Big square root. 1 minus. Christian, what was V? No, it's not what I wrote. Read to me exactly what I wrote. Read to me exactly what I wrote. What? 0.85 C. Watch. Put your pens down, look up. Christian, what was V? And then what's on the bottom of this? Also a C? Squared. Christian, do you see? Do you see? Do you see? What do you see? More specific. Rihanna, what do you see? The C's what? Do you see? That's why we did it that way. Rather than trying to do it as a number, if we can do it as a percentage of the speed of light, we'll have a speed of light on the top and a speed of light on the bottom, and they will cancel. So really what I have is this. 1 over big square root of 1 minus 0.85 squared. Get your calculators out, and I'm going to strongly encourage you to follow along with me. It is possible to do this all in one fell swoop. I'm going to suggest don't until you get good. Instead, what we're going to do is we're going to type the bottom square root into our calculator first. So open up your calculator. I'll clear my screen. I'm going to go 1 minus 0.85 squared. I'm typing what's inside the square root. And if you do that and hit equals, do we all get 0.2775? Zoom out. Square root of that. Square root, answer button. Have I gone on my rant about how you need to know where your answer button is and all this? If you don't know where your answer button is, ask me later in class. Tim, you're following along, right? And now it's 1 divided by that answer. 1 year on the spaceship, how many years back home on Earth? 1.9. Let's go back to example 1. By how much is time expanded, or is the clock slowed, if a spaceship is moving at 1/2 the speed of light? So again, here it wants us to find the time back on the Earth. If they don't give you a time on board the spaceship, assume it's 1 year. It's a nice easy number to use. Or 1 second, because 1 second will give the answer will work too, or 1 day or 1 hour or whatever. Here's the key. In this question, what's the speed? 0.5 c. So now our equation is going to look like this. T equals T0 all over 1 minus V over C all squared, and the bottom is inside a big square root. T0, 1 year, big square root, 1 minus 0.5 c over c, all squared. Nick, do you see? You see? What do you see? Hannah, do you see? What do you see? They cancel. That's the word I'm looking for. Nick, now do you see? Do you see? You see? You see? 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 How are we going to type this in? So you ready? Looks like on the bottom I have 1 minus 0.5 squared. Except, what's that inside of? Square root. Square root. Answer button. Where is that square root? On the bottom of a fraction, 1 divided by answer button. And I get 1.15. By the way, in my answer key, you're going to see I probably use the correct abbreviation for years, which is a lowercase a that I taught you from the beginning of the year, because annually. But I won't be fussy if you put 1. This, Cole, is the time dilation effect. But you'll notice, by the way, at half the speed of light, it's there, but it's not big. Although at 85% of the speed of light, it's almost 2 to 1. Next page. If we do ever develop space travel, it's going to be one way. Tristan, you're not going to want to come back. So let's imagine who will be our astronaut. Joel, you'll be our astronaut. Okay? And you're 30 years old. You've trained all your life and you're going on a long space mission. But you also have a daughter who is 5 years old. How old are you? No. How old are you in this question? 30. How old is your daughter? Okay. You're going to leave on a spaceship in the year 2000. I picked 2000 just for a nice round number. And you're going to travel at 0.99 c. What percent of the speed of light is 0.99 c? And you're going to go for 6 years as measured by you in the spaceship. In other words, from the space traveler's reference frame, T on board is how many years? How much time will have elapsed? You're going to go out for 3 years and come back for 3 years. How much time will have elapsed when you return back on the Earth? What does this question want me to find? No. T on board is 6. T back on the Earth. By the way, the tricky part with this is remembering which one's T, which one's T0. Going to make it, Emily? That's a long blink. T0 is 6 years. Joel, what's your speed in your spaceship? It's in there. Read.
99.
We can't do math with a percent.
Oh.
Got to make it a decimal.
0.99.
No.
C.
Got to have that, folks. Otherwise, 0.99, that would be like 0.99 meters per second. That's crazy slow. 0.99% of C, that's crazy fast. So what's our time dilation equation? It says this. T equals T0 square root of 1 minus V over C all squared. Or V squared over C squared. Same difference. Astronaut Joel, how long does this trip last for you? What's T on board the spaceship? How many years? Yep. Square root of 1 minus, how fast is your spaceship traveling relative to the Earth? 0.99 c over c. And folks, don't forget the squared outside the brackets. Joel, do you see? What do you see? Nick, what?
So,
What cancels out?
C.
You see? Okay. That's why we're doing this as a percentage of the speed of light. So on the bottom, it looks like, Joel, I'm going to have this. 1 minus 0.99 squared. Try that on your calculator and hit equals. Yes, you got 0.0199. What's that all inside of?
Square root.
So square root that. Is it on the bottom of the fraction? What's on the top? 6 divided by answer button. So for you, 6 years have gone by. How many years have gone by for your 5-year-old daughter? 42.5 years. So, you left Earth in 2000. You're going to come back to the Earth in 2042. How old will your daughter be? She was 5 when you left. 42.5 years have passed. You can probably do this math in your head. Joel, how old will your daughter be? Yep, 47.5 years old. How old were you when you left Earth? 30. And on your spaceship, relative to you, how much time passed? How old will you be? You will be 11 years younger than your daughter. And there's nothing wrong with that. That's how the universe works. Emma's going, whoa. Yeah. So Tristan, if we do ever develop ships that can approach the speed of light, you're not going to want to come back. It's going to be one-way trips. Someone was asking me about the movie Interstellar. Interstellar was also playing around with time dilation, but that time dilation was due to gravity and general relativity. That was allowing you to accelerate. We're not even accelerating yet. Question?
Okay. So if you're 30 and 6 years passes, so you're 36,
Yep.
or 11 years younger, whatever, will your health be at 70?
Your health will be that of a 36-year-old person.
It will be?
Because all of the electrons, all of the protons, all of the DNA, all the chemical processes in your body have also been under a slower time, a dilated time. And if you want to know why that is, it's because of quantum physics. And I can show you a video that actually gets into why that is. And it still has to do with the fact that light is, believe it or not, inside of you. Great question. Step 4. Suppose a spaceship is traveling away from the Earth at 99.9% of the speed of light. Back on Earth, 1,000 years pass. How many years elapse for those on the spaceship? What does this question want us to find? What? Time on board the spaceship. So what's that 1,000? T, just normal T, because that was back on Earth. What's our speed? Christian, can you read to me the phrase? You missed a key word after the 99.9. Okay, we got to get the whole thing. So try again, my friend. How would I write that? How do I change 99.9 from a percent to a decimal? .099? What's 100% as a decimal? Oh boy, okay. So you need to review your Math 8. If you want to do this the long way, to go from a percent to a decimal, it's divide by 100. But I want to pretend most of you can look at 99.9 and realize it's 0.99. Of, what does of mean? Times the speed of light. All right. Now, our equation is this. T equals T0 divided by the square root of 1 minus V over C squared. Except, Dylan, what does this question want us to find?
T0
How would I get the T0 by itself?
by times negative 1.
Oh, this is why I taught you all that formula manipulation. Listen to Dylan deriving a new equation without memorizing. Talk to me. What?
Times 1 over the
If we're dividing by a square root, what's the opposite of dividing by a square root? Timesing by the square root. So you're telling me yet another equation. T0 is T times 1 minus V over C all squared. This is what you would calculate if you wanted to travel 1,000 years into the future. How long do you need to go away for to come back and have Earth be in the year 3017? Okay. Time on board the spaceship is going to be 1,000 square root of 1 minus. Dylan, what was V?
0.999.
All squared. Dylan, do you see? What do you see? Okay. So I'm going to do kind of the same approach. I'll do what's inside the square root first. 1 minus 0.999 squared. Square root of that. And then what? Times 1,000. This, yeah? If I go away for 44.7 years, 1,000 years will have elapsed back on the Earth in this scenario. I will have traveled 1,000 years into the future. We're going to pick up with this a bit next class. However, questions that you can start, you're eventually going to do every question from the homework on a separate piece of paper, but you can get a head start on number 1, number 2, number 3, number 4. I skipped 5 for some reason. 6, 7, 8, 9, 10.